are going to lift, but there are a lot of such states. And just correspondingly, at this supergravity point, you also have some black hole states, which are, well, you have also some black hole states, which are basically going to lift. So it seems to be that there are, both points have almost similar looking states, which are black hole-like, and which do not contribute to the index. So this argument seems to be missing such states. So maybe those states that we are finding, those microstate geometries we are finding, are microstates for such strange black hole states. Okay, any questions? Okay, there are some other issues as well. So the pure Higgs branch, that is the invariant states mentioned in Pilsen's talk. So if you consider the backdrop of the quiver quantum mechanics, like this quiver, then there are Coulomb branch states and the Higgs branch states. Okay, so this is the Coulomb thing that Pilsen mentioned, and the pure Higgs branch thing is the invariant thing that Pilsen mentioned. And these Coulomb branch states correspond to the configurations of the multi-center solutions. And this has small entropy, and this has generically non-vanishing angular momentum. And on the other hand, the pure Higgs branch states correspond to something that's not, sorry, it's not clear what this pure Higgs branch corresponds to in the bulk. So apparently, those multi-center solutions do not correspond to these pure Higgs branch. However, these the Higgs branch states have a lot of entropy, and they have vanishing angular momentum. So what the problem is that the multi-center solutions I talked about have non-vanishing angular momentum in general, and they have some finite size, so they seem to correspond to only the Coulomb branch, and what the pure Higgs branch, which have the majority of the entropy, seems to be not captured by the microstate that I talked about. Okay, so the problem is, what are these pure Higgs branch states in the bulk? And there's some proposal about such states. Sometimes it's called a super X. So Denef, Gayoto, Strominger, Van den Leken, and Yin said that maybe, so those people said that maybe you don't have the microstate, the entropy is not coming from multi-center solutions like I mentioned, but some of the brains actually puff up into some D2 brain, which is not captured by the configurations that I mentioned. And if you take account of such D2 brain configurations, you can reproduce the entropy. So that's what those people said. And this was only at the probe level, so they did not consider the back reaction. But some people this year constructed some very basic examples of such back reactive solution. So maybe this is one way to go.
Are you taking position that single center black hole, old-fashioned black hole is not acceptable?
Sorry, can you say that again?
I mean, the old black hole solution we all know, BPS black hole,
Yeah.
strictly symmetric,
Yeah.
BPS black hole.
Yeah.
You say that's not acceptable?
That is the, okay, we want some microstate geometries.
So it's something like fuzzball type solution.
Yeah.
Yeah,
We want some kind of fuzzball solution which describe, which are microstates of the solution you just said. The single center solutions are always fine, but you want to know the microstates. And the microstates that I talked about are not actual microstates. Okay, so to summarize so far, we found microstate geometries for German black holes, in the sense that those solutions do have the same charge and mass as the black hole you want, but they are too few. So the possibilities are, well, maybe the supergravity is not enough, and this microstate geometry program is doomed, or maybe you have to consider more general ansatz. Okay, we certainly restricted the ansatz. For example, we impose the U1 symmetry, so maybe we have to relax such conditions. Okay. Questions?
The super X solutions carry singular momentum or
No, they don't.
Sorry, can I ask?
Yes.
So there's also the possibility that not just supergravity, but even geometry is just not enough. Even if you were to add stringy corrections, maybe you just can't account for all the microstates using just geometry.
Right.
Geometry doesn't see this.
By non-geometries, what exactly do you mean?
The CFT might have microstates that don't have any interpretation in terms of it might have microstates that just can't be distinguished in any sense using geometry or even using string theoretic corrections.
Right.
If you have states that differ by some e to the minus n squared terms, it's not clear that there should be a local bulk interpretation to them.
I agree.
In fact, isn't that rather likely, given that we know that sometimes it may just be that at that level, if you start asking questions at e to the minus n squared, sometimes just two different saddle points in the bulk can contribute. So it's why do we want to account for all of these microstates using geometry? I mean,
So in this case, each saddle has a geometric description, or?
well, okay. Let me give you an example. For example, let's say you try to form a black hole.
Right.
There's some e to the minus s probability that the black hole never forms.
Right.
So if you want to account for all parts of the wave function, which is what you want to do, then geometry may just not be enough. There may be no well-defined geometry that can account for the full wave function. And the CFT knows about the full wave function. So I mean, in a setup where you can account for all the microstates, why is it surprising that we don't find solutions dual to all microstates?
Well, in that example, I'm not talking about the quantum state. I'm talking about some basis of configurations which you have to quantize. So in your case, I guess, I'm going to find a Flux black hole solution, black hole microstate solution, and also a solution which doesn't have any black hole interpretation.
Well, but the basis itself has to have e to the s, has to have e to the s elements when you quantize. I mean, to be able to get the full Hilbert space, you have to get a basis of size e to the s.
Yes.
And that basis may have elements which differ in the way I just mentioned. In that there are two elements of that basis which are almost identical but have just some small, have some non-geometric differences between them.
Sorry, each saddle.
Well, it could be that one basis corresponds to a black hole and the other basis corresponds to a black hole with some non-geometric excitation on top of it, which makes them microscopically orthogonal. So the inner product is 0, but it's not clear that the bulk wave function should give you the correct description of the inner product.
By non-geometric, do you mean the CFT thing that you mentioned, or?
Well, okay. For example, you might have for example, but we could come up with other examples of things which are very very hard to distinguish using. I'm just trying to expand your point here. You say supergravity is not enough. And I'm saying it could be supergravity plus string theoretic corrections plus it may still not be enough to reproduce all possible microstates. Okay, we can discuss later.
Yeah. If supergravity is not enough, then it's very difficult to make any progress. So that's one reason why you want to go to this one. And also there's some motivation for this as well. Yes.
So is there some condition or something that we shouldn't be able to distinguish this ordinary black hole solution and microstate solution by measuring some multiple or more or something?
Yeah. As long as you're measuring some macroscopic quantities like
So you say not only the charges are the same, but also those higher for
Yeah.
multiple.
Must be really indistinguishable from the black hole.
Thanks. Please.
Or
No, please go on.
yeah, so those microstate solution doesn't have any multiple.
They do, but it's almost
Very small.
very small. So if you consider, for example, the limit where this is colliding, then the throat becomes deeper and deeper, and the multipole is really at the bottom, and it's vanishing almost.
So it's related to what you said some time back about how you have to quantize these solutions.
Right.
So if after quantization I try and pick a generic point in the Hilbert space, so I quantize it and then I use the Haar measure in the Hilbert space,
Yes.
and I try to pick a generic point. That point is unlikely to have any of the properties that any individual element in the basis has. That point might look exactly like the classical black hole.
Okay.
The question is what is the general superposition of many elements of this basis look like? Because that's the point that you would like to. A typical microstate is not any of the basis elements. A typical microstate is some general superposition of these bases.
Right.
So do you expect that typical microstate to look like any of these, or maybe to look like the one in the extreme right, where the
The typical state in the Hilbert space.
right?
It's not going to be like this. As you're right. So this is just a basis point.
Right. So typical state just looks like the classical solution. Is that the expectation? It looks exactly like the ordinary classical solution.
For classical probe.
For a classical probe.
Yes.
It looks exactly like the ordinary classical solution.
Yeah. So maybe we can go back. So you know the LLM geometries. Okay. So the microstates of LLM geometry have this kind of real complicated thing, and this is just a classical thing, and the actual typical state must be superposition of all these things. But if this is really if you consider typical, sorry, what I'm saying. So if this is really fine, then this is really indistinguishable from this guy. Any state of this type, any classical state of this type, any classical geometry of this type is indistinguishable from this.
No, I think the level of indistinguishability I'm talking about is different. I'm talking about an indistinguishability that's e to the minus n squared indistinguishability, e to the minus s. So not an indistinguishability at order 1 over n, but really an indistinguishability at order e to the exponential indistinguishability. These ones I think you could make them, dotted. There'll still be some distinguishability, maybe at 1 by s for the
I see.
triple case.
Because they are really superposing all the states
That's
using
right.
the Haar measure.
That's
I
right.
see. Okay, I agree. So maybe the indistinguishability based on such classical configuration is wrong.
Right.
Yeah.
Right.
Okay.
Be more
I
indistinguishable.
agree. I agree now. Okay, back to where we were. All right. So, okay, at least we can go to this second direction, and there is some motivation as well. So the motivation is double bubbling thing that I have been saying for some time. Okay, what are we missing? In the first place, we are missing a guiding principle for constructing microstate geometry. So we say that, okay, let's look for this one and find the most generic one. And if it doesn't work, maybe you go to this one. It's just a bit, it's just random. But it's good to have some guiding principle for where to look. So for that, let's revisit the better understood example, the two-charge system. And the two-charge system is based on the supertube transition. And so polarization phenomenon that happens in string theory when you combine some particular charges. So in the original setup found by Mateos and Townsend, we consider D0 brane and F1 brane, sorry, fundamental string. So the fundamental string is along 1, and you sprinkle D0 over that, and then it turns out that they don't want to sit there, and they polarize into some configuration like this. So this is like a tube, and the cross section is arbitrary, and this represents the genuine bound state of this system. And okay, you have D2 brane, so which did not exist in the original configuration, but this does not violate the charge conservation because this D2 is only a dipole charge. So you have D2 on this side and maybe anti-D2 on the other side. So there is no charge conservation violation. Okay, and this is similar to the Meyer's effect, but not exactly the same because the Meyer's effect is like an induced polarization, but this is a spontaneous one. And the mechanism for this is easier to understand in different frames. So if you consider, for example, FP frame, where you have F1 along 9 and P on the same, well, in the same direction. Okay, the bound state is described by F1 vibrating to carry this momentum, but this F1 should vibrate in the transverse direction, and that means that it's going to have some size in the transverse direction. And the cross section, so you have some traveling wave, and traveling wave is described by some arbitrary function, and the function is the curve that you can see if you project the configuration on the transverse space. Okay, so this is how you get the arbitrary curve in the transverse direction. And you can keep dualizing this system. So for example, D1, D5, and here you find that if you have D1 along 5 and D5 along 5, 6, 7, 8, 9, then this must go to a multiplied monopole along some new direction lambda and 6, 7, 8, 9 with the 5 direction as the special circle. So that's this Lunimata geometry. So you have some arbitrary curve in the transverse R4, and this is a Lunimata geometry, and the geometry is such that the fiber 5 is shrunk near this on this curve such that the entire space is regular. And because you have this arbitrary curve, this can reproduce the large entropy. And this is nicely explaining the origin of the two-charge microstate geometries. The reason why you have this Lunimata geometry is the supertube transition. Okay, and for the three-charge case, what happens? So you have D1, D5P, and if you look at D1 and D5, then this is the charge. This is the pair of charge that is known to be popping up into consequent multiple. And if you have D1 and P, this is simply the S dual of the FP system, and that should pop up into a new D1 brane along some new direction, and D5 and P should also pop up into D5. So if you look at this system pairwise, you are convinced that this must pop up into some arbitrary curve in the transverse direction. And this is like a superposition of three supertubes. Now, if you look at this thing again, then you find that, okay, consequent monopole and D5, then this can actually pop up. Sorry, what is it? Let me go to this one first. So if you look at this charge, these charges again, then you find that you have D1 and D5 charges, which is the same as the original one. So this can pop up into a consequent monopole. Again, now along lambda and also some new direction theta. And you must be able to do the same thing for the other two pairs, and you find that there must be some other exotic charges along now an arbitrary surface. So as far as the supersymmetry goes, this seems to be possible. Whether this is really possible dynamically or not is a different question. But as far as kinematics go, this seems to be possible. And we call this the superstratum. Okay? And because this is expected to be an arbitrary surface, this must have much more entropy easy than the super 2. Okay? And where's the slide that I was expecting? I was expecting some slide that explains what this word stratum means, but anyway, the stratum means just layers. So 2 is like after a curve, but now we have stratum, which is like a layer with arbitrary shape. Okay, and in general, you're going to have this 1, 6, 3, 5, 2, 3, which are non-geometric. So these objects are non-geometric objects, and as you go around this guy, you're undergoing some U-reality transformation. So your metric is not single valued, for example. So this is very difficult to handle. So it's good to have some geometric geometric channel in which everything is geometric. And there is such a thing. So now you can think of this like this. So let's consider D1, D5, P again. Now you combine D1 and P, then this dashed red line is going to wiggle just as before. And if you consider P on D5, then it should go into this wiggly D5 again. And if they happen to be on the same curve, then locally it is the same D1, D5. So why don't they pop up into consequent multiple again? So what you expect is that you have some consequent multiple which is wiggly, and because you have an arbitrary curve in this direction and arbitrary curve in this direction, so you're going to have an arbitrary surface. So that's what we call the geometric superstratum. And to get this, dependence on x5 is crucial. So this x5 is the direction along which this original thing was wrapped, and the wave on this x5 direction is crucial. That means that this has to be living in 6D, not in 5D as we studied before, we thought about before. And maybe this is going to be recovered this entropy. So this is a hole. This is the hole. Okay. Why do we want to discuss this? I don't know why we want to discuss this now. Okay. Oh yeah. Okay. So 2 roots to superstratum. So I explained this one. So D1, D5, we start with, and we add P to get this wiggly D1, D5, and we puffed up this D1, D5 by the original super to be effect to get to this one. But we can go the other way. So we start with D1, D5, then we get the Looney-Mathur geometry. So you have an arbitrary curve in R4, but it's not wiggling along the original x5 direction. And now you start to add momentum to make this wiggle along this direction again. This is the other way. And actually this is the way we take in later slides to construct supergravity solutions. Okay, to summarize, existence of superstrata, depending on functions of 2 variables, is a necessary condition for this to ever work. Maybe this is not going to work, but if this is going to work, we have to have this function of 2 variables. And of course, existence of such thing doesn't still guarantee this, but we have to look for this thing first. Okay, is the goal clear? Okay, so that's why we want to go to 60. So it's not like we are just looking randomly, but we just looked for what to look for, and then we found that we have to consider 60, and we have to consider solutions depending on 2 variables. So that's what we try to construct for some time. And let's talk about the supergravity side of the story first. Okay, the goal is to explicitly construct this wiggly guy, and they must depend on functions of 2 variables. So we have to redo the supersymmetry thing again in 6D. So now we have 2D supergravity on T4, and we require that nothing depends on T4, and require the supersymmetry as preserved by the original 3 charges, and we expect that various dipole charge is going to appear. Not just D1, D5 P of the original configuration, but we also have to have some other D1, D5 dipole and consequently multiple dipole. Okay, and by the way, I'm going to define light cone coordinate UV by combining T and X5. And this X5 is the compact direction that you wrap D1 and D5 on. Okay, and this solution, this supersymmetry problem was studied by various people, and the end result of the DPS analysis is going to depend on various functions and forms. So you have not just Z, but you have curly F, Z4, theta 1, theta 2, theta 4, and some one forms beta, omega. And these are going to be some functions on the base. Okay, so the explicit form of the BPS solution is like this. So it's very complicated. And there are some layers to this problem. So first, what you have to do is to give the 40 base. So just as the 5D case, you have to provide a 40 base. But now it's more complicated than the 5D case, of course. In the 5D case, you had just one fixed 40 base, which was hyperscalar. But now we have a family of 40 bases parameterized by this V. Okay, so we have this base. Now, the metric is a function of not just of X, but also V. The V is the fifth coordinate. And it's not it's almost hyperscalar, but not the standard hyperscalar, because you have some form defined on this, and you have some almost hyperscalar two forms defined on that, and they satisfy the quadratic algebra, but they're not closed, and the non-closure is specified by this one form beta. So it's some animal. It's very complicated, but anyway, so this is a zeroth layer, so you have some 40 base on which to construct your solution. And there are two layers of BPS equations you have to solve on this 40 base. So you have some first layer equations for Z and theta. So you have to solve this Laplace type equation for Z and theta. And then if you know the solutions to this, so you have now solved the linear system and found Z and theta, then you go to the second layer of equations. Now these are Poisson equations for omega and F. And the source is a quadratic combination of Z and theta. So you have, for example, here, you have some equation for omega and F. And on the right, as the source, you have Z and theta entering quadratic. It's the same for the equation for Z, sorry, curly F. So this is a linear system as the 4D case, sorry, 5D case, if solved in the right order. So you start from the base and solve for Z and theta, and they enter as quadratic combination as the source for the second layer. Okay, so this is really complicated. It's really hard to find the general solution. So what we took, the route we took was the following. So to prove the concept, so to prove that there exists some solutions which depend on two variables, we just construct some simple examples. So that's what we did in this paper. It's very difficult to go in general. Okay, so we follow this steps of layers. So we start from the zeroth layer. So we give some 40 background, and for that we start with we take the simplest one. So the simplest base is the circular linear Muffler geometry. So you have some circular linear Muffler profile, and if you consider this circular profile, then the linear Muffler geometry turns out to be pure AS3 plus S3. That's pretty simple. And you can think of this as the round superstratum is no wiggle yet, because I said that these superstrata are wiggled version